Next up, we have Faouzi Atig. Faouzi is going to talk about parametrized verification of Intel-x86 programs.
Okay, thanks. This is a joint work with Parosh, Ahmed, Kumar, and Prakash. And in this work, I will talk about parameterized verification of model of Intel-x86 programs. So I will start first by a brief introduction of Intel-x86 programs, and then I will try to explain what's a parameterized verification, and then finally our results. First, x86 programs. Usually when they program concurrent and parallel program, they assume that this sequential consistency or the strongest consistency model, where we have processes or threads that are writing to the memory, and this write or read are done in atomic manner, and all the execution of all these processes or threads are interleaving with each other. This is a very simple model and intuitive, but it allows many optimization of the hardware and compiler. In fact, modern processor or compiler, they allow some reordering of instruction, and also they use some cache and store buffer for efficiency reasons. And this has led to the introduction of the weak mirror models framework, and this framework captures the semantic of such execution. An example of this is that we have a write here, is followed by a read, and they are both issued by the same process. And now what can happen that this read will be executed before this writes. And this is what we call write-read reordering. And this is one of the reordering that's happening in the total store ordering, which is, let's say, the formal model for x86 processor. And this talk will be about TSO. And this model has been formalized in this seminal papers by Scott, Owens, Smith, Sarkar, and Peter Sewell in 2009 and 2010. And the model is, it has we have as usual some processes, some shared memory, but we put in between this processor and shared memory now a store buffer per process. And this is our FIFO queue, you can see it. So how it works, let's see an example how it works, and it will be brief. So here we have only one process, P1 will issue some sequence of instruction. And the first process, process P1 will write set x to 1. Instead of updating directly to the memory and writing the value of x to 1 from 0 here, then what would happen that this x will be added to the store buffer. It has no immediate effect on the shared memory. It's only visible for the process P1. It's still not yet visible for process P2. And then this process will issue another write. He will or she will set x to 2, and this will be added again to the buffer in some FIFO manners. And now, if this thread would like to read, and this is a combined read and test for just for explanation and to make it easy. And here, this thread would like to read that the value of x is equal to 2. What happened that this thread will first check its own buffer and see if there is some pending write on that variable. And if yes, it will get the value of the last written value write operation on that variable. And here we see that the last written value on x is 2, and this is exactly match this read and test operation, and therefore we can execute this operation. The same for the last instruction for y. We'd like to read that the value of y is equal to 0, and in this case, the process P1 will check its own buffer and see there is no pending write on the variable y, and therefore it can fetch its value directly from the memory. And you see in this case that this read operation has overtaken all this pending write operation. They have not yet reached the memory, and then it got its value from the memory. So this is why we are saying that read overtake writes. This is a very simple model and intuitive, but it does not capture somehow all the write operation of Intel. And then, of course, at the non-deterministic manner, this write will be updated to the memory. First, we set x to 1 and x to 2. And recently, there is another paper which extends this TSO model with other types of memory operation, and also non-temporal store. And this is captured, let's say, in faithful manner, what is exactly happening in Intel-x86. So we'll have different types of writes, and here in this talk, I will only focus on two, this write-back memory operation and non-temporal writes. And then I will use WB for the write-back and NTW for non-temporal writes. There are other memory operations like write combined, write through, and store fence, and other ones. But to make this talk concise, I will only focus on these two types of write operation. And we have, as usual, a buffer. Now, as you can see that I have used different color, but also I have used subscribe to differentiate between them. We have this write back now operation, and this is like the previous TSO writes exactly. It behaves in the same manner. And we have this NTW writes, and this is like the PSO writes, which is standing for the partial store ordering memory models, which is much more weaker than TSO. So let's say again an example, a simple one. So the first instruction of the first process is just issuing NTW write. It's setting Y to 1 here. And as in the classical TSO model, this write will be added to the buffer. So we'll add this Y is equal to 1 to the buffer of P1. Then P2 will write set X to 2 using write back operation. And this will be added to the buffer of P2. Now, this is the difference between classical TSO and extended TSO, what we call eTSO here, that, for example, this NTW write, now it's not anymore FIFO queue, how we update the memory. It's not the first in, first out. But rather this one, this NTW, which is setting Y to 1, now can overtake any other write on different variable. So in some sense, this is why setting Y to 1 can go and update the memory immediately. Another different behavior that, for example, this write back here cannot overtake other write back like in TSO, classical TSO, but it can overtake NTW writes on different variable. This means that setting Y to 2, this write here can overtake this write on X and go and update the memory also. And for read operation, it's the same as the classical TSO, that we first, for this process P1 will check its own buffer and fetch for the value from the last written write on that variable, and here it's 2. And for reading Y, there is no pending write on its own buffer, and therefore it will fetch the value from the memory. And to summarize extended TSO, as I said, NTW can overtake any other write on different variables, and WB writes can only overtake NTW writes on different variables. And as you expect, this leads to extra behavior and potentially bad ones. For example, if you run Decker protocol, for example, on TSO or extended TSO, the mutual exclusion property will not be satisfied, and you can end up in that two processes or two threads will be running their critical section at the same time. I don't have time to go through this example, but believe me, this could happen. So what we know about this classical TSO and extended TSO as results? Well, so what we know that for the classical TSO, when we have, let's say, finite number of processes running in parallel, that the problem is decidable, but it's highly complex. It has a complexity which is non-primitive recursive. And the proof has been done by reduction from to an extended class of lossy channel systems. And then for extended TSO, it has been shown when you start mixing this NTW and WB writes, using different types of writes, then the problem, the reachability problem will become undecidable. So, and then in that paper, the idea for which under approximation, meaningful under approximation, that we can regain decidability. And one idea that we say that for each process will be allowed only to alternate between WB and NTW. So let's see concretely an example. We have here some sequence of instruction, and we can focus only on process P1, And we can see here, we can divide this sequence of instruction for P1 into different stages. And the first stage, we can see that this process will only perform WB. The second stage, this process will perform only NTW. And the last one, this process will perform WB. This means that in this execution, for the process P1, the process P1 will perform 2 alternation, and this is equivalent to 3 stages. So if we are giving some K, and we bound the number of possible alternation per process, then the reachability problem will be, again, be decidable. And this has been done by reduction to some the partial order store ordering, which is a weaker model than TSO. So now back to the first slides, and as the title is saying that we have parameterized verification of Intel-x86, and I have tried to explain what this Intel-x86 program, semantic, and now what I mean by parameterized verification. Parameterized verification is trying to solve this reachability problem when we have unbounded number of processes running in parallel, and they are running identical code. And they are identical code. So we don't know how many will be running in parallel and a priori. And we would like to verify that, for example, if we have mutual exclusion protocol, that at any time there is only one process running its critical section. So this is what parameterized verification means. So now, what we know about results about parameterized verification. Under the sequential consistency, we know that this problem for nested processes, that this problem is X-space complete from 92, and this is a well-known result. And in Javier, Pierre, Ganti, and Drupak have worked a lot on this problem when we have no locking and no compare and swap or no test and set, and they showed that the complexity goes down and to be we can solve the parameterized verification in polynomial time. So this is what we know under a C. Now for this, we studied this parameterized verification for this extended TSO, and our results are the following. First, we showed that parameterized verification is undecidable in general, and this is by easy reduction from the finite case, because we have this compare and swap operation, and therefore we can use this compare and swap operation to select a finitely many processes to be active, and we make all the other ones idle. And therefore we can have a reduction from the reachability problem for in the case of bounded number of processes. Now, we have shown that if we use the same under approximation, which is bounding the number of alternation between the different types of writes per process, then the problem will become decidable. And here you observe that we are bounding per process, so the number of all possible alternation for all possible process is unbounded. So, and this will be the rest of the talk. So I will try to give you a brief idea. So what are the challenges in addressing this? So we have this extended TSO. Now we have unbounded number of processes running in parallel. We don't know how many. And then we have FIFO, we have buffers, which are also unbounded. And plus we have possible reordering between all this instruction between NTW and WB writes. So we have many challenges to address. And the question how we could solve this, we have 3 dimensions of, let's say, unboundedness here. So, and our approach is just to use this framework of well-structured transition system, which has been introduced in the 19th by Parosh Abdulla, Ben Johnson, Alain Finkel, and Philip Schnobelen. And this framework is some uniformed way to allow you to show the decidability of reachability. And in order to apply this framework, you need to define a well quasi-order, which is a quasi-order for which you can see it as you have infinite sequence of configuration. And for any, there will be always some index I and j such that I is smaller than j, and then the configuration Cj is smaller than Cj. And then you need to have another ingredient, also monotonicity of your system. And monotonicity means that if you are in some configuration C1, which is smaller than C2, and you know that from C1 you can move to configuration C3, then monotonicity implies that there exists some configuration C4, which is larger than C3, and also it's reachable from C2. It's some kind of simulation. This means that larger configuration could simulate any run of smaller configuration implicitly. So if you have these two ingredients, and many others like decidability of checking this ordering between two configurations, computing the set of predecessors, then you can deduce the reachability problem for such a system. Now, I would like to apply this. And it's not straightforward to apply for extended TSO, because we have buffer and we'd like to define a well quasi-order on buffer. And what we know as well quasi-order for words, because you can see the buffer as a sequence of words, is the subword ordering. And the subword ordering means that you lose some element of the word and you obtain the other one. For example, here, if you remove or delete y is equal to 1, you obtain exactly the smaller configuration. But this does not preserve monotonicity for TSO. And therefore, we'd like, because here for the larger configuration, it cannot read that the last value of y is equal to 2, while the smaller one can do it. And therefore, the larger configuration cannot simulate the smaller configuration. So, and the question how to define an ordering that allows us to show decidability of this parameterized verification. So what we do here in this paper that we introduce a new model, which is equivalent to the extended TSO under the assumption of bounded alternation. And this model, we call it NTW load. And this is a, let's say, non-trivial extension, which is DLTSO or load buffer semantic of TSO that has been introduced in 2016. And then once we have defined this new equivalent semantic of extended TSO, we will be able to apply this well-structured transition system with some more complicated well quasi-order still. I will talk briefly on it at the end of my talk. But first, let's briefly go through this DLTSO, what does mean, and this is for the classical TSO. DLTSO, you can see that TSO is just that putting writes in the buffer and delaying their execution so that reads can overtake them and go to fetch the value from the memory directly. But DLTSO takes the DL view of it. Instead of delaying the execution of writes, it will allow the writes to go directly to the memory. But it will use some load buffer here to store somehow the history of the memory so that reads can go here and fetch previous value or snapshot of the memory. So let's see an example. Here, the process here will do a write operation. Now, instead of storing it in the buffer, it will update directly the memory. And here we set x to 1, and at the same time, we add 2 snapshots to the load buffer of all the processes. And we mark here, you can see here, that I have used some marker to say that this snapshot for the variable x, it has been done by this process. Because always we need to do this last written value. If it's still in the buffer, then the process needs to read the last written value. For the other one, we don't have this marker because this write has not been done by this process. And also, you see that we keep all the history of the memory, but some of them are not relevant at all. This process P1 does not need or see this memory snapshot. And therefore, we allow that this memory snapshot to be deleted in a non-deterministic manner. And this will allow us to have this well quasi-order. And for reads, we check first our own load buffer. If there is some own written value, then we need to read that one as this read own write for classical TSO. Otherwise, we go to the oldest message in our load buffer, and here this is the oldest message in our load buffer, and the value of y is equal to 0, which is matching our read operation, and we validate it. So it's another view of classical TSO, or it's the DL view. So, and then this is equivalent to the classical TSO, and the question how to extend it now to this extended TSO, under this assumption. Keep in mind this assumption of bounded alternation. So we have bounded alternation, you remember. So here, if I see this code of the process P1, we have here does some writes here first, and then NTW. But you see that this write setting y to 4, it can be executed, it can overtake all the other writes because they are on different variables. In some sense, we'd like to allow that this writes to be executed before all the others. And this means that we need to execute this part of code before the other one. And how we do it, we just guess where each stage. Which stage is WB, which stage is NTW. And then in order to allow some reordering between all these different writes, we run them in parallel now. So in some sense, we replace this process P1 by sub-processes. So we have here, since we have 2 stages, we will have 2 sub-processes that are running in parallel, that they have each own load buffer. And if you take the concatenation of these 2 load buffer, you obtain the load buffer of the whole process P1. So, and you see that this stage 1 ends when stage 2 begin. And then also we have here, for the NTW stage, we have, let's say, like PSO buffer, one buffer per variable, what we call NTW buffer. This is because NTW can be reordered with respect to each other. And therefore, we have introduce one buffer per variable here to reorder them. But this is not enough, because, for example, you see here, this NTW on X cannot overtake all the write back on X for the first stage. So there is some kind of causality between these stages. We cannot allow anything. And therefore, we need to add some component to maintain this causality. And one of them, for example, stage 1 will speculate, for example, on what will be the last written value. And we say that stage 1 will set X to 2 at the end of that stage, and will not do any write on the variable Y. And we need to validate such a speculation or a guess. Now let's see. Stage 1 will start doing writing setting X to 1. And we are using this load buffer semantic. It will immediately visible in the shared memory, and we'll have a snapshot which will be added to the active buffer, load buffer, which is this one now. Now, as I said, that this is sub-processes, and they can run in parallel. And therefore, stage 2 can run in parallel, and then we can read the value of X is equal to 2. And then we do the NTW, which is writing NTW and setting it to 3, and then we add it to this small buffer that we have here. And then we do the next operation, and then we can see here, these 2 can go to the main memory in any order, and we can reorder them. But we cannot, this write on X cannot go to the memory because we have not validated our guess, and then we are blocked here for the variable X. But the variable Y can update the memory and add snapshot to this one. And this will become the active load buffer and not this one anymore. And then stage 1 can continue, set X to 2, but you see now this is our active load buffer. All the snapshot will be added here. And then we can validate now our guess. We have set X to 2, and this we remove this constraint now. And then we can read Y, and we read it from our own load buffer, and then the second stage also read X. And then since he has a pending write here, it will read from it. And then finally, this pending write now can go to the memory, update the snapshot, and update the second process. This is the main idea. So we use now will quasi-order, but we are using a subclass of it, which is called better will quasi-order, and this is the first time it has been used to show new decidability result. And this is enjoying much more stronger closure property, because we need to make sure that all the processes, because they have unbounded number, all of them will validate their own speculation or guess. So in summary, we studied this parameterized verification under eTSO. We showed undecidability, and we showed decidability under this restriction of bounded alternation. Future direction of work is include persistency of extended TSO, and also looking to parameterized verification with one leader or without compare and swap or read and write compare and swap operation. So, thank you.
We can have one quick question. Okay, so I think in the interest of time, we'll move to the next speaker. So the next